So the right door, the pole smashes into the right door from the pole's point of view at 16 meters, negative 42.3 nanoseconds. So, from the Barnes point of view, both doors close simultaneously, and then the pole hits the right door. From the pole's point of view, the first thing that happens is the right door closes, then the pole smashes into it, and then the left door closes. They happen in a different order. Which, there's some sense there, because I know that the right door has to close before the pole hits it, which happens in both frames. I know the left door has to close at 0 seconds and 0 meters in both frames because that's the way we set it up. But simultaneous, the lack of simultaneity kicks in again. Questions?
What does it mean if the time is negative? What does it mean if the time is negative?
It happens before time is 0. The fact that, so if the left door closes, from the pole's point of view, the left door closes when the time is equal to 0. The negative here means that these happen, from the pole's point of view, these happen before the left door closes.
You could could you add like 57.3 to the entire time?
Yeah, you could. You could. It's just the relative time of, this happens 57.3 nanoseconds before that happens.
So what happens in the other POV when the pole stops and then it's bigger than the barn, but it's also inside the barn?
So now you've dealt with an accelerated reference frame. Yeah, I wondered that myself.
Did it just expand and put a hole in both doors, or?
It would have to. Because they both close at the same time, you've got a little bit of leeway. So if you somehow stopped in that 7.7 nanoseconds, the pole would have to go through at least one of the doors. But since we're dealing with an accelerated reference frame, that's out of scope for special relativity. I'm not sure 100% how to deal with the math on that one. Okay. So we've now dealt with the fact that things don't happen necessarily at the same time in every reference frame. We've dealt with the idea that we have a way of translating between one reference frame and another reference frame. Time is not the same in both. Length is not the same in both. Let's deal with velocities. In other words, let's start out with the car and the person on the side of the road. So the velocity of the car with respect to the Earth is, we'll just say 30 meters per second. Positive. The velocity of, let's say you're in the back seat, you're throwing something up front. So the velocity, let's say, make it a ball with respect to the car. Why don't we say it's positive 10 meters per second? So from your point of view, you're in the car's still, everything else is moving around you. You take a ball and you throw it up to the front at 10 meters a second. So the velocity of the the ball with respect to the earth. Well, draw a little picture here. So this is 10 meters per second with respect to the car, and the car is moving at 20 meters or 30 meters per second with respect to the earth. How fast is the ball going with respect to the earth?
40.
From a vector addition point of view, again, it's the velocity of the object, and then the reference frame is the second letter. So as long as, when you're adding vectors, as long as the second letter of one is the first letter of the second term, you're good. In other words, velocity of the ball with respect to the earth is the velocity of the ball with respect to the car, plus the velocity of the car with respect to the earth. If you can set it up this way so that the second letter here and the first letter here are the same, then when doing addition, then you end up with ball with respect to earth. Galilean relativity, 40 meters per second. Obviously, now let's take it to a more extreme. Of course, we got Earth here. You're in a rocket. The velocity of the rocket with respect to Earth is, we'll just say 0.9 times the speed of light. You're in here playing some relativistic baseball, and you throw the ball, the velocity of the ball with respect to the rocket, why do we say it's 0.8 times the speed of light? So if I want to know how fast the ball is going with respect to Earth, well, Galilean relativity, which we know is not going to work here, but anyway, so the velocity of the ball with respect to Earth should be the velocity of the ball with respect to the rocket, plus the velocity of the rocket with respect to the Earth, which would be 0.9, sorry, doing the right order, 0.8 c plus 0.9 c, which is 1.7 c. And so if Galilean relativity worked here, we'd have that ball traveling faster than the speed of light, which cannot happen. So we need to somehow resolve that. Now, I will say it's helpful to be able to put it into Galilean terms because that tells you whether it's going to be a plus or a minus. But we'll touch back on that when we get to the formula in the end. All right, here we go. The famed S frame and the S prime frame. S prime. And I have something happening in the S prime frame of, we'll make this, keeping the same letters in my notes. So S claims a particle is moving in the distance x in frame S at a speed v. So this is some particle. So the velocity of the particle with respect to S, we're just going to say is v, which is the distance traveled over time. From the S prime frame, so the velocity of the particle from the S prime frame, they say is w, which is just x prime over delta t prime. And finally, the velocity of S prime with respect to S, we're going to let du. So I need to somehow get, since W is how fast the particle is going in the prime frame, I need to somehow connect these things. Well, we've just done the Lorentz transformation, so this change in x prime is going to be gamma x minus ut.
U or U?
U. Because it's how fast, because when doing the transformations, U is how fast an object is moving, it's how fast the frame is moving. Divided by, here, we get gamma T minus V, V minus U X over C squared. Close parenthesis. All right, we see that gamma should cancel out. And I'm going to multiply top and bottom by T. And so I get X over T minus U divided by 1 minus U over T. Actually, I want to do U over C squared X over T. Well, X over T, that's how fast the particle is going relative to S. Which I've labeled here as V. So that's V minus U divided by 1 minus, well, I've got X over T again, so that's just V, so that's UV over C squared. Connecting back to Galilean relativity. If I want to know the velocity of P with respect to S prime, that should be the velocity of P with respect to S plus the velocity of S with respect to S prime. Again, getting these the same. Velocity of P with respect to S is V. The velocity of S with respect to S prime, well, the velocity, if S says that S prime is going that direction at the speed of U, then S prime saying S is going in a direction that way, the speed of U, negative U. So in Galilean relativity, the velocity of P with respect to S prime would be V minus U, but in special relativity, we have to have this extra factor on the bottom. These signs will be the same, they're both negative, and V and U are at the same speeds we have up here. Likewise, if I want to know what is the speed of P with respect to S, which is the problem I have over there, then that should be the velocity, should be the velocity of P with respect to S prime plus the velocity of S prime with respect to S. So in Galilean relativity, it would be W plus U, V equals W plus U. But in special relativity, it would be V equals W plus U over 1 plus UW over C squared. And so now, let's do it. So the velocity of B with respect to the Earth is going to be 0.8 c plus 0.9 c over 1 plus 0.8 c times 0.9 c over c squared, which is 1.7 c divided by 1.72. And we have a number that's going to be less than the speed of light, which is fortunate. And we end up with 0.9 something.
Like 988.
Why don't we take a break here, small little break. Let me decide what I'm gonna subject you to next.